Good evening, everyone. Welcome to this special edition of the NITheCS colloquium, not on a Monday, not at 4. Yeah. Nevertheless, we are very happy to have Professor Lee with us this afternoon, straight from Harvard. Yeah. So welcome to Stellenbosch. And there is Professor Toby Lowe with us, who invited Professor Lee, so I will ask him to kindly introduce our speaker. Yeah.
Good. Thank you, everyone, for joining us this evening. So I'm very pleased to introduce Lina as our speaker today. So just quickly, I'm part of the South African Council for Automatic Control, which is the national member organization of IFAC, which is the International Federation for Automatic Control. And IFAC appoints 8 distinguished lecturers for a 3-year period. Now, the first time they did that was in 2020, so 2020 to 2023, but due to COVID, the distinguished lecturers didn't really have an opportunity to travel. So, Lina, I'm correct in saying you were part of the 2020 to 23? Yes, okay. So, Lina was appointed as distinguished lecturer in 2020, but we're fortunate that she is still able to travel. So, IFAC supports this initiative to get really prolific researchers across the world to give us some more insight into the work that they're doing and what they find interesting. Now, Professor Lina is a Winokur Family Professor of Electrical and Engineering and Applied Mathematics at Harvard University. She received a bachelor's in mathematics from Zhejiang University in 2007 and a PhD from Caltech in 2013. She was a postdoc at MIT from 2013 to 2014 and has worked at multiple institutes, including MIT and Google Brain. Her research lies in control, learning, optimization of networked systems. She has been associate editor for multiple journals, including IEEE Transactions on Automatic Control, Systems and Control Letters. And I can start naming the awards, but it'll take up too much time from her speech. So we're very pleased to introduce Lina to give us a guest lecture. Thank you.
Thank you. Thank you for the invitation, and thank you everyone for coming during the evening time. So I try to make my talk as enjoyable as possible, try to reduce equations. So my background is in feedback control, and recently I've been studying, like I would say, for more than 7 years, doing more data-driven learning-based control. So the work I will talk about is start with a collaboration with Google Brain. I did a sabbatical in Google Brain. You look at the Google, those people that actually from computer science background. So we start the collaboration saying how we can make reinforcement learning, which is applicable for the physical dynamical system. So let me do a very quick motivation. So like I don't need to motivate much. With the growing exposure of the data, image data, language data, we see the success of the deep learning. And even like couldn't help, like yesterday I had a list picture is a Nobel Prize in physics given to the deep learning. And then today the Nobel Prize chemistry given to the AlphaFold. Like I put in those just say we see the advantages by having more data with the explosion growing computation power, we can really see the impact of how deep learning has been doing. So now I have been working on like several physical system, which has a physical system has a sensor for a long time. So if you look at another, like in our physical society, so we also have the exposure of data. We have more and more smart devices, and we call like Internet of Things. The device is capable of sensing and actuating, like this is kind of the projection of how many devices are going to have. Like on average, probably by now, everyone has 4 to 5 connected devices. So with those kind of IoT devices, with those kind of data, we start visualizing the future of our urban society. We have smart house. We're going to have the new transportation system, which even don't rely on the traffic signal, that we can talk to each other. The manufacturing is definitely going through another industry 4.0 transition. And for the healthcare, we have so many smart devices. How about using the data to do better diagnosis and including the treatment? So those are very nice visions. If we take a deeper look from the feedback control perspective. So how many of you has ever taken a control class? Raise your hand. Great. So now let's look at from the feedback control perspective. We have a physical system. We have sensors, and the sensors will monitor the situation, send the data to the super powerful computer at the edge device or data center, and we'll send it back to the actuator. So when we look at the picture, the feedback loop is fit into our 101 class nicely. But we took a deeper resolution to see what's really going on with the difference. Is first, the numbers of the devices is much larger compared with the traditional class book examples. And we have the sensors, actuators deployed spatially, like in the system. The devices are sending like real-time streaming data. Even we say we have a fast communication scheme, compared with the data amount, the information technology is still limited. We're going to have the limited computation on the edge device, have limited communication power from individual device. And on the other hand, since we rely on the connect devices, on the one hand, we want the connect devices to help each other. On the other hand, they also introduce fluctuation, impact each other. So what this says is, even like a lot of control in the classical textbook, we rely on the model-based control method. But once we look at the smart city, the big system, like what's really the model describing the interaction, it's actually very difficult to build a model describing what's really going on with the system. So I put in a kind of gray box here. What that means is like it's getting harder and harder to model it. So that's kind of why, like even from the control society, we would like, hey, since we have the data-driven method, how about we go ahead and look at the data and using the data to figure out the control strategies. And take a reinforcement learning as an example. Right, the reinforcement learning example is has a control agent, has an environment. Based on the environment, control agent can observe the state, fit into our control textbook example very nicely. And control policy, the smart agent taking the action, and how we're going to figure out the action is go ahead to based on the reward, how the system is performing. So if we're doing the learning-based control, typically the framework is go ahead to have policy, test the policy, getting the reward observation, go ahead to update the policy. So you look at here, the reason I would say why a lot of people actually got excited, not just from the typical engineering background community, including the science, biologists who actually didn't really do much math before, they will say, oh, I can use this method because I don't really need to understand what's really going on with a black box or gray box. I can just keep retraining the control policies. But now, once we dive into it, is look at the exciting news. Of course, right, since the AlphaGo, we had a lot of successful news about deep reinforcement learning. Even including the large language model, the final tuning will rely on some reinforcement learning to do the final tuning. But the bigger motivation, like let's come back to our engineering physical systems. We want to transfer success of the AI, like if you back to this pictures, I say the one common thing is everything is doable on the computer data center. It's purely computational. And now let's look at this picture. It's not just computational. It's not just based on the computer to compute the decisions. I put in some example of the physical system. Right, for the power system, we have the power grid. Trying to determine if you take control action, you have to kind of rely to wait for the entire power system to see what's really the response of it. And people are excited about potential of the robot to helping people's daily life, to do the elder care. And transportation. And the last one is actually one project that hopefully have a time to talk at the end of the talk, is a recent collaboration with a biologist. We're trying to grow a bio organ, like out of any kind of living bodies, and how to use a smart sensors that my collaborator have been designed, figure out the stimulation policies. So the common thing for those, like the difference is now it's a physical system. I can only stimulate change. I cannot just decide if that's me just driving the control decision, the state from like 1 to 1 million immediately. It's not the case. And let me dive into more of the challenges. There are many challenges, and the talk I will focus on kind of 4 challenges I will touch base. First, about data. So we know the success of the deep learning is based on the huge amount of data. This is the image data, and this is the ChatGPT, the large language model data. And now let's look at the physical system. The reason we get excited about potential of the smart devices is to do something new. What this means? Well, do we have a data which is don't have, for example, for transportation? Do we have a data to see how people really react without traffic signal? And what is the way we're going to do? We actually don't have the data. And taking the power grid example, one reason actually the power grid want to improve is because climate change, the emergency weather conditions, I want to figure out a better way if some emergency happen. Again, what's emergency happen, at least right now in the US, typically we'll just do the rolling blackout. But that's not really the way we want to do. So putting here is a very limited low quality data. It's expensive, and it's also even we don't have the data for the things that's not exist before. Now, diving into the sim-to-real gap, like for some system, we actually have a lot of data, like for the single robot lab, and we even have a simulator to do it. A lot of reinforcement learning papers will having those videos showing in the back, in the end of the paper. But now we dive into the real physical system. So one is actually for my own physical lab, and the other just if you search on YouTube, you'll find a lot of videos that's how the robot is going to fail. And like the reason is always a gap, right? No matter how you're going to improve your model, it's always not going to capture the entire system. And now about safety. This is one pushback, frustration I had when I work with the industry. It's because safety is always the most critical thing. If I have been working on power system for more than a decade, I want people to use my algorithm, not really learning algorithm. I had a like guarantee, had a performance guarantee, a simulation, but it's very challenging because they worry about if some bad things happen, you're going to trigger a blackout on the entire city. And can you guarantee that? Like I guarantee in paper, it's hard to know in practice. So this is like the safety is very important. Well, actually holding a lot of things back, but what should we do? So last one, the scalability. Since I mentioned like a potential to improving the system is to use the connectivity of the devices. And what this means is even we think we have a super powerful computation, the GPU, and this is in the big data center. And now when we want to do the smart decisions, we have the smart edge devices. So we want to figure out a way, how can individual devices, based on the current local information, to take immediate action if something happens. And this is actually very challenging. If we think about scalability, this is a different dimension of a scalability compared with doing things on the data center. So with those motivation, like I don't have like just one clean answer. Oh, hey, this is the method. Go ahead to try. You solve all the problem. If we had, that'd be nice. Like so far, we don't have that. And I would say for those who have engineering physics background, will always come to say all the system has structures, right? All the system also has the domain knowledge. We spend a lot of time to figure out how to the way to operate the system. Can we actually explore some structure, domain knowledge? And today's talk, I've actually focused on the mathematical part. Is kind of general, I would say representation. And you will see later how the representation can be adapted to different application. Like kind of provide a framework people can plug in the domain knowledge into the system to do control. I'm not sure what I have time to dive into some concrete examples that I've been working on, which is what further zoom in the challenges for individual application. So feel free to ask me questions during my talk because I do want to making sure everyone follow this math equations. And it's totally okay for me not going to finish. Like yesterday I was doing the talk and it was University of Victoria. I was only able to, let me show you, finish the part one, part two. I was later sure I was 3 components, I only able to finish 2 components, but which has great discussion. So now let me kind of dive into, I will focus on the mathematical part, representation system structure. So what do I mean by that? To set a common language, I will using some math notation to guide the method explanation. So this is the standard kind of control problem. When we open the nonlinear control textbook, we'll see this problem or stochastic control textbook. So we have a system state. I'm using the S, represent the state, not the X. So we have a control action. We have the system dynamics, well guided from one state to the next state based on the control action. So the system always has disturbances or noise current to perturb it. We have the reward function, and to making the problem well defined, we can either do the limit discounting factor, you can do the limit averaging, or do the final time horizon. The outcome is to figure out feedback control policy based on the current state, what should be the control action. So if I take in this example, in case there's some audience who was not having from the control background, this is the card inverted pendulum, which is a example I always use to teach my student in class. It's for here, if you think about the control action, you have inverted pendulum, you actually can move around. So that kind of force putting on the cart. And the state is going to be the position of the vehicle and the speed of the vehicle, and also the inverted pendulum, because the goal is to making sure the inverted pendulum is keep upright position. So it's also including the angle of the inverted pendulum and also the angular velocity. That's kind of state and control action. So like with this one, I want to highlight is for all those kind of problems, those F, it's not going to be linear. It's depending, like especially for the example I showed before, it can be highly complex of the F function, it could be nonlinear. So I was a PhD student in Caltech in the control program. like trying to learn tools, right? Is there any common tool to solve all the nonlinear control problem? Unfortunately, it's not. Like if you based on the system structure, we have a different kind of method, and the some method is general but computationally very expensive. It can probably only solve the system with 5, 6 states, and probably also give very different solutions. So like including some of the SOS programming and recent the Kuhlmann control, a lot of papers trying to figure out, can we making the nonlinear system become a linear system to do the control? For those who actually had this kind of experience, all the method has limitation, especially the computation. So the motivation for this talk and also for my collaboration with the Google brand is, since reinforcement learning community kind of doing a similar problem, so can we like even don't argue whether we should do RL for control or not? Like since RL had a lot of computation algorithm, people can just grab and to test. So can I just even use in the RL as a computation tool for the nonlinear control? The first question. But even don't worry about the data. I have a classical nonlinear control problem. Can I use in putting like grab a toolbox from the RL community and to see whether I can get a control policy for those nonlinear system? And then why I want to do that? Like, how many of you have tried to train the IO policy using your own laptop? I got 1, 2, great. So if you haven't to do it, I should recommend we actually provide one toolbox to make it easier for the control community, like to starting train the control policy. So like for those trying to try, right, at least because the community, they actually provide a lot of code, the GitHub, grab something, replace it to look at outcome. I will tell you the frustration, like when I started the project, how frustrating it is when I just grab a toolbox. So what I will talk about is first part is, let's just think about using it as a computation tool to do the representation-based control. And then I will talk about data. Like the reason we do it, because we want to handle complex system, we not necessarily have the model. And the last component, I will also talk about how this representation can be adapted to handle the large-scale system. So as I said yesterday, I was only able to finish part 1 and part 2, which is okay. So feel free to ask me questions. Now let me dive into the part 1. So what exactly do I mean the representation-based control by using reinforcement learning? Now I'll give a quick review of the reinforcement learning language. It's actually very similar to the problem, the notation I described before compared to nonlinear control. We have the time, which is you can call the stage or you can call it time. At each time you have state, you can take control action. And now this is kind of one of the difference when people describing the state transition. So in the state space model I used before, we use the state space model from STAT to the ST+1, you're adding the noise. And the MDP, macro decision process, directly model the state transition at the transition probability. You will later see one kind of highlight this one. And state reward, the same thing, you are describing how good the system is running. Policy, same goal, objective function, similarly, by use the policy, follow this state transition probability, go through the long-term reward by taking that policy. You can look at it, this is almost the same as a nonlinear stochastic control problem I was describing before. So what's really the IO method? Like, I'm not going to dive into the details, just in the high level. Regardless what kind of IO tools you're going to grab, it's kind of having both feature, one's actor, one's critic. What the actor trying to do? So I have a different color in the back, and I think the screen not really showing my color. So apologize if you didn't really see a better visualization about how the color is making the difference. So we have 2 blocks for the actor. So for the actor, it's trying to figure out how to update the policy. So now let's think about the complex nonlinear control problem. No one knows what should be the optimal control policy class. Right? Should I do the like sine, sort, nonlinear function, polynomial function? No one knows. So again, like that's actually the neural net can play an interesting, important role. It's okay, since I don't know what to read the parameterization, similar to the deep learning, let me just parameterize the policy by some neural net architecture. People can pick their favorite one. The easiest one is always go ahead to do the feed-forward, fully connected network as a first step. And now once I have this policy, and figure out how to update the policy. So connection with the gradient descent, this is the policy gradient. But for the policy gradient is when we think about even the policy is linear, and since I care about long-term reward, I try to writing down the value of the reward of gradient is actually impossible to get analytical solution. So the way like the famous theorem is called a policy gradient theorem is you don't need to really compute the gradient using this one. Try to use the gradient using the reward, the Q function. So what the Q function is? The Q function is just a long-term reward. If I start from the state and action, try to evaluate how good my policy is, and substitute into this policy gradient theorem, I can know which direction I should head into. So it's called a policy gradient theorem. So now it's here, like for this algorithm to work well, I need to figure out what should be the right cost to go, a reward to go on the each S and A. If you have a continuous state control action, this is like really a large table, like infinite dimension table. So then what people would suggest is, okay, so since I only have a limited amount of data, or I can only run the system limited time of time, let me try to also parameterize the cost to go by grab some neural net and parameterize it to something. Again, you can pick the feed forward neural net over that good starting point. So now, if you look at this one, I had a two-part. This is the one biggest question. The method, when you're doing the interloop, you probably can also get rid of one interloop, focus on one loop. That's a Q-learning. But then when we look at this one, is one big frustration for people who is not familiar, or like for people who don't have much experience, like me, to tune the neural architecture is what the neural architecture I should really go ahead to start. But which one is the right one? I would say there's a right one, like which one actually will give me a better training learning experience. So that's the frustration I had. I was studying, tuning them. I was not able to really, like this is a few years ago, but its success rate is actually pretty low. And I got a student like who I was suggesting him to work on this research area. He's spending half a year, couldn't really tune some neural net well for the IO problem. Then he decided, okay, I'm going to go purely model-based approach. I'm not going to do IO. So that's the kind of frustration people have. And so the question we pose here is, can we have a systematical and a simple way to come up with a parameterization of the neural net? And I know for this kind of neural net, I have a systematical way to probably add the parameters of picking what to read the function class. That's kind of the representation I will focus on during today's talk. Now, so the answer I would say is called a spectral representation for the critique. So this, we have ongoing work talking about active parameterization, but today I'm not going to talk about active parameterization, just about the Q function representation. What should be the QW, the kind of neural net parameter or the architecture should they use to making sure that you can approximate the true Q function well. Hope the question is clear. Good. So now, let me, like this is actually the most important slides for the entire talk, is what the key. The key point, like when we dive into what exactly is going on with MDP, a lot of learning methods kind of, it's not really just like do the Monte Carlo simulation, you adding all the reward up. As you can, for example, we can do the Bellman recursion based on the current state action. You take it one step. This is a reward to go for the following one, say transition probability, current reward, and this is a Q. So this kind of called a Bellman equation. A lot of methods is trying to minimize the equation error and figure out the Q. So if I look at this equation and put in the key fact, if I have a way to write my state transition, this is state transition, into an inner product of two feature functions. One is the VSA, the current S and control action. The other one is the next state. If I have a way to write in this probability distribution, conditional probability distribution, in this inner product form, you can substitute this one to here, and the integration is actually has a linear property. What it says is a Q function actually sitting in the same feature space of the VSA. So I say the reward function, typically when you design a system, you actually have the goal you want to achieve. You know what the reward function. So like this one, look at here, what's the feature space I should start with? If I have this feature function, and I know my Q function is linear with respect to this nonlinear features. So now if I back to the learning problem, like to learn the Q function, now I know what is the space the Q function should stay in. I'm using the data. My job is just to go ahead to update the omega, which is kind of least square programming problem. Like we have a guarantee about optimality to know what is the optimal omega explaining the data. So indeed, when I was studying this problem like 3-4 years ago, you look at the time of the papers, they have a lot of efficient IO algorithm, even starting from the theoretical point of view, how to, if it has this structure, how efficient the method can be, how much like the dimension of dimensionality can be mitigated if I have this decomposition. So this is nice, but when I was studying and read those papers, I got one confusion: is where this decomposition come from? Like why a system has this decomposition, or what really the feature function really means. So it's good for the theoretical analysis if I start with that assumption. But if this assumption I can never refine the system to have this kind of decomposition, then what the use of it? So that's a big motivation to start the question, like what's really like, it's just a pure assumption that actually I can connect with my physical system. Now that's the next slide. Let's dive into here. So it turns out, at least like look at here, almost all the nonlinear system, by following some real analysis, I can match to the decomposition. And putting this is a state space formula we are familiar with. Let me just writing it as the state transition probability. If this is Gaussian noise, then this is satisfying the Gaussian kernel, like the S prime, FSA. This is just the norm distribution. So why I'm doing it? Now, this is the positive kernel. So for machine learning community, there's a lot of work on the kernel learning before the deep learning took off. So for the positive kernel, this is the definition. You think about positive definite matrix is similar. You have a 2 input, x prime. No matter what, it's going to be a positive function. So why talk about this? Let's block my equations for the picture. So for here, this is from the real analysis, the decomposition theorem. So if it's the positive kernel, and we can find the one feature function, which actually the Fourier random feature psi omega, to decompose the kxx prime to the inner product of this. And the norm of the inner product is defined as this expectation, this norm distribution, this way. So now let me connect both of them. What it shows is my state transition probability can be written down as a positive kernel. I put them together. So what I got psi omega FSA, psi omega S prime. Now connect with the decomposition I showed before. This is actually my feature space, PSA. And here I also got another feature space, psi omega S prime is a mu S prime. I will come to the mu S prime later. But now remember for the previous slides, my Q function is sitting in the same space as phi SA, and phi SA is actually this function. Now, if we talk about if I have a knowledge of my nonlinear system, right, which means I have the FSA, it's not like throwing your knowledge away. I can use in my FSA, and the last kind of the neural net layer is becoming the cosine sine layer. And that's actually kind of should be the representation. At least this representation, I can theoretically guarantee it can cover all the state transition that I'm interested in. So put in summary is the non-stochastic nonlinear control I was showing has a linear feature decomposition. And this is the feature space I can start with. Any questions? Good. But there's a caveat. Like from the real analysis is very nice decomposition theorem. But the one caveat is I'm aiming for a computation tool, right? Even not worry about theoretical guarantee, just a computation tool. But this is infinite dimension. Like this is integration among this is a norm distribution has infinite dimension linear feature decomposition. To compute, I need to figure out the finite choices of the basic function to go with. So there's a different tool which you can use. There's a random, and there's also a nestrom here. So the random feature representation in the next slide is you just, since this is formal probability distribution, I can just random draw the feature according to the rho omega distribution. And the nestrom is similar to the single value decomposition. You try to pick the top features. More computational heavy, but if it's offline control, you actually can get in those kind of offline bases ahead of the time rather than putting on the online computation. So let me dive in for the random feature representation to show the example. Right now, connecting every component, we can write the state transition into the linear decomposition. And I just need to sample the feature according to the random distribution, and this is going to be the feature I'm going to use. And the QPy is linearly approximated by that. And if I start with tooling, for example, you can start with like 200 features, and you end up the performance not really that good. You can add the feature, just adding more random feature into it, and you will see gradually how the performance is being improved. And later I will show, even combined with the learning problem, how we systematically add a feature to improving the performance. Any questions? Feel free to like ask any questions. So now for the algorithms, it's actually pretty straightforward. Right? I'm not really changing the IO algorithm. I'm just talking about representation of the policies of the Q function. So take whatever the IO algorithm, that's your favorite one, just change the code about how you're going to represent Q. So you change the Q using the feature you had, like from the knowledge you learned from the dynamics, and then just follow the same dynamics, same IO algorithm you did before. With that, like, let me show you the performance. We try to benchmark, for the paper, we actually benchmark with the classical control method and also this IO method. So let me show you the compare with iterative LQR. I guess probably most of you had some experience doing the LQR for the controls people and the like recent improvement. So the one big challenge for those methods is if I add noise perturbation during the dynamics, it's actually very hard to find a policy which you can actually swing up the unit pendulum. And this is we also did before we run in the real simulation. So we did run the real physical demo. We did a simulation on the drone. And for the drone one, we actually systematically show if I go ahead to add the feature and how the performance is getting improved. I want to compare like for the toolbox, at least the one we grabbed from the computer science community, they always will start with 2 hidden layers, fully connected neural net. Each layer has a 256 parameters, and this is like 256 square parameters you need to tune if without kind of think about representation. And this one you look at here is only kind of 4,000 random feature. The random feature are easy to get to do the random representation. And we got this result preliminary result last year. We got a challenge from control professor is trying to ask us, can you actually benchmark with even more classical method and also Pandelbot? Because in the 1990s, there was some competition among control community and trying to figure out what is the best controller that we can do for the Pandelbot. And you can actually use a lot of physics informed way, which is energy-based method. So we did it and to see how our method will work for the double Pandelbot, like with also Acrobot in the OpenAI gym. So you can look at the energy-based method. I would say it's indeed did pretty well, especially when they don't have a noise, because people are really optimizing the whole trajectory by using energy-based method. But once you add a noise, this is what I'm saying. Is for many classical methods we have been tried, once you add a noise, it's actually very hard to tune the control policy will work robustly against the different noise level. So with that, I will say kind of finish the first part of talk is another advantage why we're doing it is we don't want to treat it as a black box. So we want to have some theoretical guarantee to know the performance gap. So for this performance guarantee, you can imagine we had approximation on the Q function. So that's this one, feature truncation. So when we update the Q function, you want to have the model. The better way to make it efficiently is to using a dynamics as simulator. I kind of fit into either the Bellman equation update to find the parameter W of the Q function. So there's a statistical arrow here. And the last one is a policy iteration because you have to terminate algorithm kind of step. So for if you're interested in theoretical guarantee, so everything is in the paper. I'm not going to talk about that part. And there's also extension, like for engineers, we care about safety, robustness. So those are kind of ongoing work. For the robustness, is we simulated, we had our own robustness algorithm. So we simulated getting the controller by like a certain norm mass is the inverted pendulum example, and then you can change for the real mass to a different value. And with our robustness version, this is like not really including the robust version, you can see the performance better. And the safety is that if my objective is not like the reward, let me say there's a certain kind of region which is safer, and I want to find the controller to go to the safe region and then stay in the safe region. So, and this is like we had based on the representation I showed to you, and this is kind of the method being the outcome. So I'm not going to dive in detail for this one because I want to move to the data-driven part, which is how this representation actually can also connect with the data if I don't have the knowledge of the F. Any questions so far for the model-based one? Yes. Yes. Yeah. That's a great question. So theoretically, like if you check the paper, so we had it will depend on the problem, like the state dimension, control action dimension, and also the property of the FSA. So that kind of theoretical guarantee, and we'll talk about depending how what absolute guarantee you want to have, and then this is how much data you need to put. And that's the kind of theoretical guarantee, you can try to follow it. But similar experience, like I was also doing optimization before, like I will do the analysis to making sure I kind of know the algorithm has some guarantee. But then for the real system, the experience, as I think that later part 2, you will see like how we really do in real life, right? In reality, I will start with some feature. For different system, to be honest, you wouldn't really know how many features exactly you actually really need. You will start with some number, and then you will try. If you see like typically performance is not really that bad even at the beginning. So, but then you can gradually to add one or more feature once you have one or more data. So you will see like in the part 2, I actually particularly address how can we adaptively add in more and more feature. So in real problem, my answer will be it will case by case, depending on the problem, you will figure out what is the best one you can have. We can always kind of using the guarantee from theoretical guarantee, which is more conservative. Yeah. Thank you. Any other questions? Yes. Hold that question for the second part. We'll see. Okay. So hold that question. Great question. Other questions? Good. So now let me dive into the data-driven part, right? So about how we can actually gradually add the feature, right? What's the advantage for the representation will provide if we want to add features. So now once we have like the data-driven one, if we don't have the model, it's a straightforward way. The standard way, if we using the system identification, is first try to learn the system by using the tools we have been developed in the system identification community. So then follow into the feature decomposition, and taking the policy. It's kind of one straightforward idea, I say model-based learning. If I dive into it, right, I'm not really using this one much when I train my policy. What I really used is the decomposition. So I can also go directly from the data to the feature. So why have this one? I would say this is I wouldn't say it's kind of the model free one because I still have a model. I'm go ahead rely on the state transition probability model rather than the state space model. So what are the advantages of doing it? Let me dive into this part. I was actually very excited to like this year because I had this semester like for a couple of years. I want to like, what is really going on with the representation, and is it have a bigger connection? So first straightforward method, if we think about, like I said, this is connection, it's kind of similar to those kind of matrix decomposition, right? If you think about you have a tensor, 3 input, SA and S prime, you can do the tensor decomposition. You force yourself have a tensor decomposition, be the phi SA, mu S prime. So then you can use the standard spectral density estimation, loss function, finding it, doing the singular value decomposition, putting this way to do it. So this is kind of more follow the decomposition like mathematical idea. But let me highlight is what really we learned here is a probability distribution. So for the probability distribution, why I want to highlight it? There's a lot of like method being developed, I would say in the deep learning community, especially for the generative AI. The generative AI what it's been trying to do is to generate a data point which follows certain distribution and you don't know what the distribution is. So if I connect with that, this is a learning problem about to learn the probability distribution. There's a difference is now I'm trying to learn the conditional probability for the state transition. So first straightforward idea from the text probability class is I can do the maximal likelihood estimate. But if I try to figure out the better way, making the sample more efficient, there's a lot of recent progress is like, for example, contrastive learning. You can just kind of bootstrapping using some noise model. This is your real data, you have noise model, try to figure out representation to differentiate your random noise model, at least from your data from your real system. So this is a high-level contrastive learning. It's actually a lot of different kind of computation tools. Some will be had an advantage in the compute list problem. And since I've connected with that one, there's also score matching. A lot of algorithms people have been developed. The score matching is, let's don't worry about the P, look at the gradient of the P, and this will provide additional computational advantages. Even further, you can also connect with the diffusion models. So if I connect, like rather think about state space model representation. think about state transition probability, I have a lot of computation tool I can connect. And then regarding the question, like how much data I need, what's the performance guarantee? Again, so I would say those reference essentially I carefully put in the reference here. We read more of them, and those papers that I really appreciate. I get a lot of inspiration by reading those papers. So I would say this a lot of things actually can be done here. If I think about certification in terms of identify state transition probability for our dynamical system, we can do a lot of things to connect with the generative AI with our control dynamical system learning. I feel interesting. Obviously, this is still open. Like you can still come with your new method. My student recently got another method that you can put in here using the Fourier features I was talking about before. So once we connect with this, now there's still one difficulty when we don't have the model. It's about exploration, right? If we don't, because I have a limited amount of data, then put in the model. So if I just use in my historical model, it will be very biased. You just go ahead to learn what your data can tell you. So always for those reinforcement learning, we'll add additional exploration thing. So for the exploration, so it's actually you can use in the way that you like to do exploration. For example, Thompson sampling is a popular one. I would say it's actually straightforward one to use. And putting a class of function you want to learn, make it be like doing the Bayesian update, and then random draw F to put in the feature, and then getting the policy. Or another way, rather than do the probability distribution, I can each time, based on my uncertain quantification, to add a bonus function to encourage the control policy also getting additional new data from it. So this is the high level. Like it's a high level looks straightforward, but the details are actually pretty difficult. For the real demo, we can have more discussion about for the real demo I will show later. So what exactly we do? So this is what we did for the simulation. Simulation is relatively straightforward to be done because you actually can do the exploration at what you want. You don't worry about the question system, just keep learning it. Now, let me talk about the real physical demo, like from the simulator out to the real physical system, right? How the representation actually can help me to gradually doing better. So the sim to real gap for today's talk, I will focus on the gap between the transition probability, since my representation is focused on the transition probability. So we know like this simulator has a dynamics and the real system based on the so many disturbances happening in the real system. We will never be getting the true dynamics. So this is the real robot has the real dynamics. Like when I talk about the feature learning, but their feature is not necessary to be the same one. But this is the advantage we put into the linear space representation, like linear with respect to the nonlinear features. Now you can think about the knowledge you learned from the linear vector space, kind of similar story. They're just on the function space. So from the simulator, I will learn the phi naught, and my Q, reward to go, will sit in the same space. Now, this one cannot really cover the true because the gap between the P and the P naught. So in the real world, that's why I put it into the linear feature representation is you can just have the P minus P naught. That's the difference. And the difference, you can have the similarly decomposition structure. So if I think about the linear vector space, if they have bases, not enough, I'm going to have to add some new bases. So the question is how we can really learn the new feature efficiently rather than kind of pretend I don't have any kind of feature to start with to improving the efficiency of learning. So the idea is very similar to the linear vector space learning. It's from the function space viewpoint, dive into it. Like originally from the simulator, I learned futures, the function fitting the span of the space. Now I need to figure out a new features. And it's not really the new feature. If I want to improve in the data efficiency, then the natural way, if you think about the Graham-Schmidt procedure we learned from the linear algebra class, is we're going to impose some orthogonal constraint. Right, which is like since if the previous feature already capture those dimensions, let me try to find a new feature which cover orthogonal spaces. And it can definitely answer one question is what is the definition of your orthogonal? So this is also a rule you actually can play with. For us, because we have limited data from history. So based on the data, we put in the data, the way to judge is follow the linear decomposition, the norm space we talk about. and then put in this kind of condition based on the current data. But the exact orthogonal is kind of more like the insight, inspire we put in this orthogonal constraint than to improving the data efficiency. So this is the high level picture. That's how we think about close the loop from sim to real, or even like you had training from past data. Now you had a new data coming, how we can adaptively learn the new features. So put in this procedure from the physical simulator, I learned the feature. I said for this learning the feature, you can use in so many different methods, not necessarily this method. And I put in the initial policy, put it on the controller, and deploy it. And you will see like it's not really going to do very well if I don't do any adjustment. But I got the new data. For the new data is once I come, I will also update the feature, then put in the learning method, also update the control policy, keep doing the feedback loop. So that's the procedure, and we follow the procedure. That's interesting that we are not showing. This was showing before. Okay, good. So this is the drum experiment we did. It's actually a simple task, just powering at the target position. So the first policy, just take the policy from simulator, then to the real drum. Now here we actually follow another paper, did a one skill transfer is you get the new data, but you can update your policy rather than to update your feature, just update the policy. It's doing better, but like still it can fail. So the listed from our algorithm is not just like it's in the paper we showed how many rounds of new data collection we did. It's not much. Even for the entire physical demo, the student was able to finish everything within a week. Like once we have our algorithm, everything ready. So we did this demo just within a week, and eventually we got this kind of stabilizing policy. And then we were talking about, can we, so, but this is the trajectory, the final detailed data. So we asked the question, since I trained the policy in some environment, now if I really fly the drone outside, right, it's a windy situation, it's actually not really the same as even the data I collected before. So how robust it is, or can I actually do those adaptive lifelong learning, keep tuning it? So that's motivated us to do this task. Okay, come here. Good. So the baseline controller is a controller I showed you before. And then now we're putting a fine here. It's an old fine. Some lab member left when they leave the lab. Now we add a wind. But you can see that once I add the wind, it's definitely not going to do that well, but it's actually not that bad. And so since we see now once you fly your drone, you always collect the new data. I can always go back to update my feature. So then we're actually using that like this is a third round. So we actually just collect 3 rounds of data and put in the control, like it's doing better. And then we want to test now, since I trained my policy under this kind of new situation, how this controller going to do if the wind situation is getting changed. So we manually change the wind speed. I actually want to probably buy a more expensive one and putting a stronger wind and to show how this drone is able to really sustain with even stronger wind. So you can look at here, it's actually doing pretty well because after the third round, we actually got a lot of information we got before. So it has a fit out control policy, which can do well under all the different windy situations. Questions? Yes.
Just use the mic as requested. So I'm interested in a couple of steps back. You spoke about skipping the models, going directly from the data to the feature space. But one thing that the model does is it gives you the opportunity to impose physical laws and physical constraints. And there's almost a level of regularization that you achieve when you go through the model to the probability space. So it speaks to the bias variance trade-off. So don't you lose some of that when you get straight to the
So I think that's the advantage of why I want to do the representation based. That if you recall the first part of the talk, the model based representation, right? Where the model will show up is the psi omega. Okay. So it's a very fancy addressing to the screen situation. So the psi omega bracket FSA. right? That's actually where the knowledge of the FSA showing up. So if we like for the pure model base, that I know putting the F there. For the gray box, right? Sometimes we have some knowledge, but some knowledge we don't have. The advantage of doing it is I can still pick in this kind of representation, the psi. If I have the model structure of the FSA, but this is some parameter in the theta, I don't know. So I can put in the structure the psi omega F theta SA. And once I have a new data, I'm going to update the theta value. So that's the advantage. That's why I'm interested in the representation. It's kind of something between the model frame and the model base. It's not like skip the knowledge we have. If you have a knowledge, figure out what's really how it's plugged in into your feature representation. So I got some audience. They come from computer vision, perception control background. They also want to try to use it because in their mind, I guess, they will think about the layer, like the psi omega, kind of last layer you're going to put. And the FSA, they can even go ahead to do the perception based. You can put in the computer vision, call that as a feature, and then adding additional layer, and that's your entire state representation. Yeah. So that's the for me the advantage of by doing this way is connecting the connection. But so far for this demo, our model starts with the simulator, so we actually didn't really put in the big giant F there. And we had recently trying to test more even for the data-driven one. Because when I represent the psi omega FSA, if I don't know the FSA, I can post my neuron architecture into this form and to show the advantages. Like the preliminary result, now showing the talk, indeed it actually will show the advantages. It will learn quicker, faster. Yeah, thank you. Any other questions? So I want to highlight for this one, it's kind of has a online interaction with the physical system, but that's kind of what's called the sim to real gap or the lifelong learning. The last one, let me show you another real demo. This one so far we were only able to do the offline version yet. So there's some questions, theoretical question about how much the diversity of data you need to be. But let me dive into what's really the imitation learning we try to answer. So for the imitation learning, the one I said for the reinforcement learning, is I have a reward function and just go ahead to play with it. You have the online interaction. It's actually very positive, dangerous. I'm always looking at the video, the robot dog is actually from my colleague. They haven't really used it yet, and we actually used it before they started use it, and we're actually doing things like this to the dog, and hope my colleagues not mad at me. So, but you can see it's actually quite robust for the robot dog in the lab. So for the expert, the imitation learning is, there's a lot of things which you can learn. For this one so far, the simulation I'm going to show to you is we put in the built-in control policy, come with a robot dog, this is a unitary robot dog. They have a different version of the control policy that you can go ahead to start with. It's just you don't know what's going on with the control policy. They didn't tell you that. But you can press a button, and this is the expert policy, and it's doing pretty well. So now for us, if I have an expert demonstration, so can I just go ahead to figure out a way to design a policy, making the dog look like that? The problem with putting in, this is the imitation learning, the reward function. It's different from the reward function I showed to you before, because it's actually even hard to say, what exactly do you mean a dog walking like a dog? So then the way we said the walking look like a dog is we have the expert policy, and we look at how the state look like. And then this is from my policy, I want them to look similar to each other. And when you define similar to each other, so for this problem, we just say the walking, so we can make him be like a stationary distribution. They call it state occupancy measure, like the state distribution that will look like the expert state distribution. So that's what we put. So the thing I want to highlight is a recent paper we just submitted to ICRA. So the thing I want to highlight is I have been kind of talking about the feature we use about VSA. That's another feature we got, mu-s prime. Right? So far we haven't reused it yet. For this one, it's actually we use both features because the mu-s, the other feature we got, is actually can tell us where the state occupancy density function will sit in. So we using both features we learned from the data and then put it into RL algorithm solving the imitation learning. Now, let me show you the demo. It's actually easy to, the simulator is actually pretty straightforward to do. We got no problem to just test our algorithm on the simulator very quickly. The real demo actually took us at least more than about 10 days to making the control policy real functional on the real robot. There's another question I would put in the open discussion at the end of the talk is about, my talk was focusing on the cost to go, the reward representation. As everyone here who had the control experience, the control policy representation is also very important, right? Depending on what kind of control policy you start with, you probably will never really get to a solution. So that's what happened here, is we spending a lot of time like trying to figure out what should be the actuated representation. And for the robot dog, now we had one and more experience. We know what really we want to do. We had a 52 state as input, and the control action, what for this robot dog, the demo I show here is actually the joint position as my control output, and then put it into the robot dog and to see how it's going to work in. But to figure out that policy took us a while. That's actually what working well on the real robot. So like I said, this is offline, but offline means you got the expert data, you try to mimic what the expert doing. There's one limitation so far is what my robot is able to do is kind of limited by the expert data. So I can make it the robot dog right now working like a robot. If you tell me, can your robot dog like go to a target position as quick as possible? If my expert policy, like the data didn't have that one, so if I cannot guarantee that. Like right now, the demo I showed you, is just my robot dog can walk straight forward. So there's a like challenges in the mathematical side, like what's the challenge for the online learning, that if I wanted to getting more, I need to figure out the exploration. So for the exploration, I probably need even once I did the one demo and probably asking the expert to do some other actual thing. So this is the open question, like to put in that. So now I actually finished the second part, questions. Probably, yeah, almost close my end of my talk. Yes. Yes. Yes.
So my question was, you mentioned about safety in the second part, also the first part of your talk.
Yes.
I was wondering how the representation kind of helps to guarantee the safety of the learned policy. Thank you.
Yes, great. That's a great question. To be honest, is depending on your safety constraint, right? Wouldn't say we have a tool that can handle all the safety constraints. And the safety, like the first part talk, what I was showing, if my safety, I know if my, it's totally okay, like if I just stop now. So the safety criterion, right now we can handle if I put in there's a target state distribution, like certain kind of state is unsafe, certain state is safe. I can make it my outcome of my control policy will kind of follow the target density distribution. That one can use as representation. And then if I have some other, like if all the time you want to stay maintain certain thing, that will be harder. So there's a one thing I didn't talk about, like since the talk I talk about representation, like of the state dynamics. So there's a, you actually can do a lot of following work. For example, this one can also working together with the MPC, the model predictive control. So you can put this as a safety constraint, and rather than writing down the ST, the state space model, writing down the dynamic state transition, and definitely I think the safety constraint I need to have is become a trans constraint, right? You not able, if depending on the randomness, there's always some like small probability you probably will hit. So that's a mathematical answer. In reality, I would say the answer will be, if especially for the safety critical thing, in my opinion, this that I was sharing to the audience as well, it's better to have some like safe policy that I know that if something happen, I can do the risk mitigation, right? So correspondingly, the mathematical tool I need to have is I will have a way, I need a way to kind of categorize the risk associated with the current state and action. If I see the trajectory is heading, that you cannot just stop when you see the system becoming crashed, right? You should probably switch back to the safe control policy ahead of time, right, to leave the time for the system to adjust. So that will be, in my opinion, like in reality, that's the solution I will go ahead to do. And then the question about the trade-off between the exploration, like the getting improved of efficiency and to guarantee the safety. I figure the like the soft point. Thank you. Other questions? Yes. 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 Do you want to ask more questions? I can also go quick to talk about high level of the next part, the network. Just like 2 minutes. Yes. So this one actually will skip the model that tell you the motivation. Right. Come back to the motivation I talked about beginning. Is we're going to have connected system. Even for the building, this is a building from our Harvard. Like my current office is really huge building. You have a lot of sensors. And this transportation, You can have congestion, you have the dependence of the nearby roads. Now the big question is, how are we going to find a control policy to do it? And the control policy, can you imagine, I can already do the centralized policy, send it to a central command, especially for the transportation, will be time consuming. It's very dangerous, consider all the communication delay. So the talk, let me actually jump into the just one slide of the summary for this part work. Is going to the summary of the method I want to highlight is this. Like, we need to figure out a way. There's two representation. For this one, I should talk about two representation. One is a control policy representation, how many hop of neighbors information can have. And the other one is, when I put in my local control policy, I also need to figure out a way how good the system is doing based on the current policy, but everyone has the local information. So I need to figure out a way to evaluate the policy by using the neighbor information. And I will talk about the representation for the cost to go, the reward to go. I need to figure out a way how to re-evaluate the cost to go individually by using the local information. But with the data, you probably even can get in some local understanding of your dynamics. But how those kind of local modeling of the local dynamics able to help me figure out representation of the queue. So that's kind of the main ideas of the third part of the talk. And we are writing the ICLR paper. Now I think the deadline is tomorrow. So once the paper online, like I'm happy to share. So we have a like, systematical way to talk about local actor and local critic. So I would say with that, I can close the talk. And but I want to show this with picture. This one we actually do the linear system. This is about local controller. This is what I want to highlight. This is the optimal controller using all information. And this is, I do the truncation. So we had a 50, like kind of ring network 50 agent. So this blue one, if you look at here, is a fully local policy and only using the local information to evaluate the policy. And this is how good it can be done. And I only need to make it the red one, only 3 hop of neighbors information. I'm able to even approximate the global optimal solution nicely. Like another demo about the synchronizer. Similarly, we can just using, the one I want to highlight is by using my representation, our spectral critic, they can do much better compared with just like putting into the deep neural net, like don't really think about representation. And we have like hopefully the paper will be out in a week, and then everyone, if you have a large scale system, so you probably can try this representation. So with that, I would like to conclude my talk. So I've been talking about the representation start with the change the state transition probability to this decomposition, where it's coming from, how we can connect with the data, and how we can connect with the large scale system. I already talked about a lot of like ongoing future work. I'm very excited because it's actually really can combine the theory and application and combine with the physical knowledge. And like, I'm happy to explore collaboration. If you have the chemical process, I want to see like how this system is going to perform. Feel free to reach out to me. Thank you. We have been doing different applications. Thank you.
Thank you very much, Lina. I think we might have time for 1 or 2 questions. Any questions from the audience? Sure.
In the experiment where you were putting wind on the drone,
yes,
you were changing wind styles, and
yes,
it was still. What would have happened at that stage if you moved the angle from which the wind blew at the?
we didn't do it. That's a good idea. Yeah. That's a good idea. Yeah. But also like putting the drone outside in the windy day in Boston, that would be also interesting experiment to test. We haven't really done that yet. Thank you.
Any other questions? Okay. Well, I think we'll be in the foyer for probably 15 more minutes if you would like to speak to Lina in person. But once again, can you just please say thank you to our distinguished lecturer? Thank you.
Thank you. Thank you, everyone.